here's a quick video covering calculations for a compound gear. Alright, so chances are for your project this week, where we're looking at using the stepper motor to drive some gears to pick up an object, you're going to probably end up using a compound gear in some form or fashion. Okay, so a compound gear just means you have a pair of gears sharing a shaft to help you figure out your gearing mechanism. Okay, so we're going to use the same gears that we had in the kit. All right, so I had the yellow gear that had 10 teeth. There's the pink gear that had 50. There's the green gear that had 30 teeth, and the blue gear that has 40 teeth. So the way I've drawn this picture here, the green gear and the pink gear share the same shaft. All right, so they're going to be, rotating at the same speed because they're on the same shaft. All right, and they're going to have the same torque because they're sharing the shaft. All right, hopefully that makes sense. That's the key assumption on analyzing compound gears. All right, so in this case, we're going to assume that N1 is the driving gear. All right, so we're going to take a look at N1 and assume that it has a certain speed, all right, so 100 RPM, and a certain torque, 30 Newton meters. So this is driving. And what I want to do is calculate the output torque at gear 4. So I want omega 4, the torque and the speed, and tau 4. All right, so that's the goal of this problem. All right, so we take a look, and I look at first the interaction between the yellow gear and the pink gear. All right, so what I know is that the speed changes according to the gear ratio. Okay, so I look at this and I'm wondering if it's obvious to you. If the yellow gear, which is smaller, is rotating at a certain rate, okay, it's going to make more revolutions than the pink gear, okay, because it has fewer teeth. It's going to spin faster around for the same, because they're interacting at the same tooth spacing. All right, so doesn't it make sense? You don't really need to look up the formulas and try to make sure you have the N1 and the N2 on the top and the bottom in the right way. Doesn't it make sense? You could just look at this and tell what the speed would be. All right, so it's a smaller gear driving a bigger gear. The speed of the bigger gear is going to be smaller. All right, so I look at the pink gear. The speed of that shaft that is on the pink gear is going to be the ratio of the gears, 10 to 50, times the shaft speed that's of the driving gear. Okay, so I do that and I get 20 RPMs. All right, now I can also do the same kind of idea with the torque. All right, and then the sort of the mental shortcut that I use here is that I realize that if you drop the speed, you increase the torque. All right, that's the law of an ideal gear. All right, so we're dropping the speed here. We knew that, so that's going to increase the torque. So I start with a torque of 30, and the gear ratio is 50 to 10. So I get 150 Newton meters for the torque for the shaft of the pink gear. Okay, so now keep in mind that the green gear, which you might call gear 3, is on the same shaft, so it's got the same speed as gear 2. It's also got the same torque because it's the same shaft. All right, so that lets us move forward. We can now look at the interaction between the green gear and the blue gear. Okay, so omega 4 is the blue gear, and again, the green gear is smaller than the blue gear, so the blue gear is going to be rotating slower. All right, so omega 4 is omega 3 times 30 over 40. Okay, because 30 over 40 is a number less than 1. And that would slow this down, and so I know omega 3 is the same as omega 2, and omega 2 is 20 RPMs, so I substitute the 20 here. 20 times 30 over 40 is 15 RPMs. All right, and then I can look at tau 4. Again, I went from a smaller gear to a larger gear, a smaller driving gear to a larger gear. All right, so I take the torque on the shaft that's connected to the green gear. All right, remember tau 3 is the same as tau 2. Okay, so I take the 150 and I make it a bigger number, 40 over 30, which is 200 Newton meters. Okay, so that's a quick walkthrough of some calculations that use a compound gear, and in this case we're assuming ideal gear, so we're not worried about the efficiency of the gear just yet.